Okay, so let's discuss this method called logarithmic differentiation. This addresses questions as follows. Let's think about this function here. Now, before we go on to talking about derivatives, let's think about the function itself. We have to worry about whether this is well defined, because you can't just take any number and raise it to any power. There are certain situations where that doesn't work. For example, if this base were negative, well, we can't raise negatives to fractional powers, because that would lead to complex numbers, and we're considering here only real valued functions. So we need to make sure that this is never negative. We also need to make sure that this base is never zero, because we can't raise zero to negative powers. After all, that would be dividing by zero. So very importantly, we have to make sure that this base is always positive. And conveniently, this function x squared plus 1 is always positive, so no problem. Okay. All right, so with this function now understood, let's proceed to the question, how would we find a derivative of this function? Okay, so lots of students will look at this and notice that, hey, we have a function to a power, and we have a rule called the power rule. And the power rule, this is the generalized power rule, where we have a function to a power. Power rule would suggest that we proceed like this. Now notice I put the question mark here in recognition that we're considering whether this will be valid. Okay, so let's give it a try and see what happens. Well, following this rule, I get that, and a little bit of a simplification gives me this. Now, is this okay? Can I do this? And unfortunately, very much no. You can't do this. This does not apply, because the power rule, this generalized power rule, requires that the exponent be constant. But look at our function. This exponent is not constant. So the power rule just doesn't apply. Okay, so don't make this mistake. It's a very common mistake for single variable calculus students to make. This answer here is wildly wrong. Okay, so this problem, we have an exponent here that's not a constant. We have an exponent that's a function. Well, a lot of students will then think, okay, well, let's use the exponential rule. After all, the generalized exponential rule addresses what do you do if you have an exponent that is a function. So here's our generalized exponential rule. Following that rule, we would get this. Is this the right answer? Well, very much unfortunately no. So this doesn't work either. The exponential rule requires that our base would have to be a constant. And look over here at our function, this base, not a constant. Right? It too is a function of x. So the exponential rule doesn't apply either. This answer is wildly wrong. Okay. So, well, we seem to be in a bit of a fix. How can we resolve this? Well, that's the subject of this talk. It's a method called logarithmic differentiation. Logarithmic differentiation will resolve the need to differentiate functions that look like this, a function to the power of another function. Now, again, in order to make sure that this expression is actually well defined, we do need for our base to always be positive. Not allowed to be zero, it's not allowed to be negative. Let's just avoid those problems. And then we need u and g to both be differentiable. Okay, with that assumed, then here's the strategy. We'll see as we go through an example why this strategy works so nicely. This is our logarithmic differentiation method. Three-step process. Step 1, take the natural log of your function. Step 2, differentiate. Turns out, we'll see this in a moment, that taking the log makes that highly possible. And then when you're done, solve for what you're interested in. So let's see how this applies to our example. Okay, so let's take the derivative of this function, same function that we considered before. Now you'll notice I have the question here phrased separately. I did not give this function that I want to differentiate a name as written in this example. And sometimes that's the case. Right? On the other page I did give it a name, but anyway, previously, in some such situations it might not be given a name. If it does not have a name given, give it a name. You're going to have a name for it. So call it f, take the natural log of both sides, and we get this. So very importantly, we need to have a record of what we've got here. So you have to have a name for it. Okay. All right, and of course this simplifies, right? Rules of logarithms turns that into that. Okay. Now, step 2, differentiate. What makes us think we're going to be able to differentiate? The whole problem was that this expression is something that we don't know how to differentiate. How can we all of a sudden say just differentiate? Well, this is where the log, taking the log, has done us a favor. In this step, having taken the log, notice that while we previously had a function to the power of a function, using the properties of logs, rewriting this, I no longer have a function to the power of a function. Right now I simply have a product. And we have a rule for how to differentiate a product. So, moving along, differentiating, capitalizing on the fact that we've gotten rid of the exponential, differentiating is no big deal. And here it is. Now we have to use the product rule. We do have two factors here. The product rule says that first you differentiate the first factor. Second, second you differentiate the second factor. So here's the derivative of that right-hand side. Now, of course, we also have to differentiate the left-hand side. Now, on the left-hand side, keep in mind, this expression here, this is no longer f. This is log of f. Right? We took the log of both sides. So, differentiating on the left, we get that. Don't forget about the chain rule. And taking the derivative of a log, you get a reciprocal, but because of the chain rule, you multiply by f prime. So, we took a log of both sides. We then differentiated both sides. And now, going back up to our method, the very last step, solve. So, what are we solving for? Don't forget what we're interested in. We're interested in the derivative of f. It's specifically f that we want to take a derivative of. So we want to solve for f prime. Notice that what we have written down here is not f prime. Right? This thing right here is not f prime. This is the derivative of log f. Not what we want. We want the derivative of just f. So conveniently, the derivative of f that we're looking for, well, it's right there. It's very easy to solve for it. All you have to do is take this 1 over f, cross multiply it over to the other side, thus giving you f prime. Here's that f that we've cross multiplied over to the other side, and f prime is this. That's all there is to it.